Okay, so what I'm going to do for you is do like video notes. So you obviously got your grade 9 notes that you can look at, but sometimes it's nice to have someone talk you through it. So we're going to be looking at electricity. The first thing we notice from electricity, the beginning, electric. Well, we know that must have something to do with electrons. And that's exactly what electricity is. It's the movement of electrons. So there's various forms of electricity. You've got static electricity, where electricity is confined to an object. And then you have electricity in a current, where you have a wire and you have the electrons going around the wire. You also have electrons that are attached to some sort of an element, which we call an ion. So we'll get to that. Actually, let's start with that. So knowing that electricity is to do with ions, let's start with what is an ion? An ion. Well, we know what hydrogen is, right? We know the element hydrogen.
Yeah.
A different color, hydrogen. Now, when hydrogen is in kind of the atmosphere or whatever, it's in the form of a gas called H2, hydrogen gas. So when we're thinking of hydrogen as a gas, it's H2. Now, when we look at hydrogen in our periodic table, it's the first element. So hydrogen is the most common element in the atmosphere. Actually, sorry, in the universe, because it was the first element. And we know that in the sun, you have a lot of hydrogen fusing together, hydrogen fusion, to become helium. And that fusion reaction is exothermic. It releases energy. And so we know that there's a lot of hydrogen in the sun burning, becoming helium. And so hydrogen is very common and important, highly flammable. And that's because it's the reason it's flammable is it's highly reactive. And our hydrogen ion is H+. I don't want to go too much into the chemistry of this, but just know that hydrogen is H+. And if hydrogen is H+, that means that if it's got an electron, so hydrogen sits with one electron, okay, which it usually donates. And so because it often donates an electron, it becomes plus. So the ion is plus because of the donation of its one electron. If we look at the other side of the periodic table, we would look at group 7 to kind of explain an ion, the chlorine ion. Now this chlorine ion has 7 electrons, and something about our elements is that they like to have 8 electrons, called the octet rule. Aside from hydrogen and helium, which are in the first group, which just have the first orbital, most elements which we deal with until matric anyway want to have 8 electrons around them. And because chlorine has 1, has 7, it actually wants to have an electron. So if we were to color hydrogen's electron slightly different, just to distinguish it, we often would say, well, hydrogen could donate its electron to the chlorine, and so you would have HCl, which we know is hydrochloric acid. Okay. Getting slightly sidetracked, the main thing is that your Cl is an ion, is a minus ion. Okay, so the main point about this is an ion is an element that has a charge. Okay, so it's not like H2, which is a gas. It's sitting alone and it's got a charge. So chlorine has a charge. And so what does this mean? Well, okay, we know that Cl minus has a charge of a negative. If you go into the kitchen, you'll see something called salt. Now, salt in the scientific definition is not just table salt. There's a lot of different salts, but let's think of table salt. Table salt is sodium chloride. Now, what is interesting about sodium is it's in the same group as hydrogen. And so it's also got this plus ion. It's got this one extra electron that it wants to donate. So if we have sodium and chlorine together, they would look a little something like this. I'm going to draw my sodium electron in pink and my chlorine electrons in blue. And what we notice is that the sodium donates, and then the chlorine kind of has a full orbital. Sodium loses an electron and actually downclasses to the nearest noble gas, which is the one in the previous group. But as I say, I don't want to go too much into that. I just want to talk about the idea that sodium and chlorine, this salt, when you put it in water, it ionizes, meaning the sodium and the chlorine ions separate. And so if I have a solution like this, and I put this salt in, I turn this around, and I put a bit of salts in here. Into the solution of H2O. My sodium ions and my chlorine ions separate. I'm not going to go too much again into the way that your water surrounds the chlorine ions. But it's to do with the fact that water is called a polar substance. And polar is like you have the poles of a magnet. It has a positive and a negative. Because of this positive negative property of water, this polar substance, it is able to separate the sodium and the chlorine ions. And what you end up having is this ionized solution, okay, this Na plus and Cl minus ions in the solution. So they're no longer, just sort of in the form of salt, like when you have salts in your salt shaker, it's crystals, okay, it's NaCl crystals. When you put it in water, they separate into their different ions, okay, so the sodium becomes a plus ion and the chlorine becomes a minus ion. And we know that if I'm thinking about negatives, I'm thinking about electrons. And so when we're thinking about ions, we must think about electrons, because what makes something an ion is just the fact that it has a charge, and this charge is due to electrons. We know that the positive charge comes from the nucleus, where you've got protons, but the electrons are important, especially because we're looking at the electricity section. Why are electrons kind of more important than protons? Because the electrons are the things that are doing the moving. So when something gets charged, the electrons move. The protons do not move. Okay, so it's only electrons that move. So electricity, movement of electrons, ions, movement of ions. So if you have an ionic solution, it can conduct electricity, which is quite interesting. So you could have here I have my ionic solution here. What I could do is let me do another one. Okay. I don't actually need to do another one. I'll just do the same one. I'll just use the same one. And so I could put a couple of, these are called diodes, or anode and cathode. Okay, or electrodes, what you're calling it. And so these electrodes could be connected to a battery. So I haven't drawn this too clearly here. Let's do the plus. Let's do the slightly shorter one. So that would be negative, and that would be positive because it's longer. And this, if I put this in water, it completes the circuit because the electrons are allowed to flow. The electrons are allowed to flow. Okay, so let's draw the electrons in a color we haven't used. We've been doing them in light blue. So let's keep them in light blue, although I put the water, we'll put that water in dark blue. Okay, and so let's put the electrons in light blue. These are then, because these negative chlorine, that's just, we could think of those as its electrons, these ions. And so this electrons are allowed to flow around this solution, which now is a nice way. It's going to bring us onto electricity. I just want to quickly talk, when we get into the circuit, about the flow of electrons. When we talk about conventional current, I'm going to repeat this again when we do electric circuits, but conventional current goes from positive to negative. So if I have my positive side, my long side, conventional current says that my electrons go this way, okay, in the direction of the red arrows. But electrons do not flow that way. So this was one of the big mistakes in science, is that I think it was Edison thought that the electrons moved from positive to negative, but actually they discovered that they are moving in the other way. Because they move at the speed of light, they it was impossible almost to detect at that time what direction they were going in, because it felt like they were going one way, but actually they happened to go the other way. So electrons are actually flowing from negative to positive. So the red arrow is what we call conventional current. But I'm going to go through that again when we get to our circuits. And just to remember, the electrons flow the other way. Electrons flow. Electron flow is from negative to positive. Okay, so if they got it right the first time, we wouldn't be dealing with this issue. We would just call it the flow of electrons, and there would be no conventional current. But unfortunately, this positive to negative conventional current that we use by convention cannot be changed, because electricity is one of the most dangerous things around, and it is a convention, and all the electricians around the world, they all use conventional current, and so it's kind of just too late to change. All right, so that is our ions. Oopsie. Let us now go on to let's look at another aspect that we need to know, which is an electric field. So again, we're still talking about electricity. Okay, now, because you have an electric field, so now we're going to sort of go away a little bit from our kind of idea of electricity and the ion flow and more about a charged particle. Okay, now what we need to know for grade 9 is that you can have a positive and a negative charge. Okay. A positive and a negative charge. Okay, and what Einstein found was that these charges have an electric field. And Maxwell also, before Einstein, did a lot of work on charged particles. And found that from this charged particle, you have an electric field. Okay, so it's a little bit like the starship in the Starship Enterprise in Star Trek. You have this starship, and around it is its force field. Okay, so if you are sitting in this force field, in this field, you will experience a field, but it's there whether you like it or not. So it's not like a force, because a force from Newton's third law says that every force, force has an opposite reaction. So if I push the wall, the wall pushes back on me. This is something different. This is an electric field. It's not a force. We'll be dealing with forces just now, forces between charges. This is just the fact that there is a field around a charged particle. Positive goes outwards. Now, the direction of this field, these field lines, is very specific. They say the direction of these field lines, the direction of the arrows, is the direction that a positive point charge would experience. Okay, that's important. Notice that from a positive charged particle, the arrows are going this way. And what do we know about charges? Well, we know that opposites repel and like charges attract, right? So here's the positive going away. So it makes sense that if your lines are, by definition, what a point charge, what a positive charge would experience, what direction the positive charge would move if it was in this field, of course it would be repelled. And so that's why there's this negative, there's this outwards direction. Another way to think of it sort of visually is you have a positive charge and it's sort of positive going outwards, right? Positive going outwards, and then negative. If you remember that the positive is going outwards, the negative goes inwards. Okay, so this is a fairly common question for multiple choice. They may ask you A, B, or C, which are the direction of the field lines. Okay. And so here, of course, if we put a positive point charge in here, by the way, this person could just be a pointer. It shouldn't really be a person, but something in this field would just they would experience a field in there. And so we know it is positive, opposites attract. So our positive point charge would go in there. Okay. All right, so these can now interact. So I've almost actually can leave this here, because notice that, look at these. They both go in the same direction. And this is something that we will notice. I'm going to do a little highlighter sort of thing, but our point charges can interact. And notice that they're both going in the same direction. And so this might be sort of said to be going like that. Okay. And so if you go to your grade 9 notes, you will notice that you have this idea of a positive and a negative. This is how the field lines would be between a positive and a negative charge here. Okay, does that make sense? You'll see this in your notes. That it's very common in grade 9 notes. Okay, so we started with those point charges. What directions do they go? The positive goes inwards, negative, positive goes outwards, negative inwards, and then if they interact, this is how they would interact. And so now I want to look at the forces.
We've done something similar with.
What's that?
We've done something similar with magnetic forces.
Great, great, yeah. Well, magnetic is nice, right? Because it behaves in the same way as these things, right? Magnetic opposites attract like poles, repel. Electricity and magnetism are incredibly closely linked. I know that I can create a magnetic field using electricity. I know that I can also create electricity using magnetism. So I think you'll get to that either later on this year or in grade 10. But you'll certainly notice that if I wind a whole bunch of wires, electric wires, and then I take a magnet and I push it in and out of those wires, and I put a voltmeter connecting those wires, you'll actually notice that there will be a current starting to flow in those wires when I push the magnet in and out. If I keep the magnet still, the current stops. But if I move, and it's the movement of this magnetic field, I'm getting sidetracked, but that is called induction, and you induce an electric current. Okay, but let's get back to what you need to know, which is forces between charges. I don't know if you need to know the equations. I'm just going to give them quickly. But your electric field, and as I say, I don't worry too much about this unless we come across it. But there's an equation, KQ over R squared. Now, what's interesting about this equation is that if this is the electric field and R squared is at the bottom, as the R gets bigger, so R is radius. So as something gets further away, notice because R is at the bottom, the electric field gets smaller as the distance gets bigger. Because think about it, 1 over 10 is much smaller, bigger than 1 over 100, right? 1/10 is 100th, 1/1,000,000th is tiny. So as this R gets bigger, your electric field gets smaller. And that we can see visually, because the strength of this electric field is based on how far the lines are. So if you think of a person sitting here, he's going to experience a larger electric field. His electric field is larger than over here, because it's kind of, you can kind of see that the distance between the lines, if those represent field strength, it's much more, it's much smaller. It's kind of, if you think of something being diluted in water, it's quite concentrated at the center, and then as you go further and further apart, it gets weaker. Now, when you talked about you doing something similar with magnetism, when you have a magnet and then you have metal iron filings, notice that as you get closer to those iron filings, then suddenly those iron filings lift up and get attracted to the magnet. But if I go further away, you notice that if I hold them, and then I can actually feel, even if I put the metal here and the magnet there, I can feel it starting to pull as I get closer, and then it snaps together. As I get further away, that magnetic field strength gets smaller, just like this electric field gets smaller as you go away from the center. So I'm not going to go into this equation. K is a constant, R is the distance, Q is just the size of the charge. But the main thing is that it's getting smaller as you go further away, and that's represented by those field lines. So whenever we look at field lines, the more field lines in a space, the stronger the electric field. Okay, so let's look at the force between charges. So this is slightly different to electric field, because electric field just is there regardless of whether there's another charge. So yes, we say that if there was a point charge inside the field, it would get attracted to the center, but it doesn't need to be there to be a field. Just like on the Starship Enterprise, your force field protects the ship at all times. When you go close to the thing, you will notice that it's suddenly there. It's like an electric fence, right? It's there regardless of whether there's someone touching the electric fence. Now, when we look at forces, we need to have an opposing force for it to come into play. And so this we look at as two charges, the force between two charges. Okay, so I could say, what color did I use? Plus, and I use plus for. And so let's say that we have a charge here, plus, and a charge here, Q, minus. Now the symbol for charge is Q. Okay. And so I can have something like Q1 and Q2. So Q1, Q2, and this would be negative and positive. Now, if I've got two charges, they experience a force, they place a force on each other. Okay, so we say that the positive, when it comes outwards, a force there. So this charge experiences an attractive force. They